Did Daniel text you or call you yesterday?
No, one second. Hey everyone, can you guys hear me?
Yes.
Yes.
Okay, so we're going to have a quiz next week well, actually, I'm going to probably post it on Canvas either Tuesday or Thursday, but it's going to be take home. It's going to be on dot products and cross products. So yeah, that's going to be the quiz. Are there any questions that people have about the homeworks or about the material?
How does the homework grading work exactly?
How do they grade it, or how it will work out in the end?
How it'll work out in the end, like when it's converted to Canvas, I guess.
Right. So each one of the homework problems is worth like 300 points. And so they're all basically equal. And then that's how the grading will be determined. There'll be a certain number of points in the end, and we'll see how many points you got out of those points. Yeah.
Okay.
Okay, so I'm just gonna stop the video for a second because I'm not gonna have my video on because I don't have a tablet right now, but okay, so let's continue with example 6. So they gave us the following example. Second. Yeah, sometimes the whiteboard does this. So 1 second. Okay. Fine. Let me try to stop sharing the screen. And I don't know why this whiteboard is not working. Sorry, 1 second. Okay, here we go. So the first line was the line R1 of t is equal to 1, 0, 1 plus t 3, 3, 5. So this is R1, and then R2 of t was equal to 3, 6, 1 plus t 4, -2, and 7. So we're trying to figure out whether these two lines intersect. So if they intersect, we would have that the x-axis for both, so x of t, would be equal. So that's 1 over here plus 3t, so 1 plus, and we're going to call this t3, t1. This is going to be the parameter t1 for this line, and this line is going to have a parameter t2. And yeah, if here are your two lines, so this is one line, and here is another line. then each one of them has some parameter for their t. So that this one would have t1, and as t1 grows, you move along the line. And the other line is going to have the parameter t2. So maybe that's over here, and as you move t2, you move along the line. So yeah, t1 is going to be for the first line, and then we're going to have that this is equal, and then we're going to look at the x-axis for the second line for R2. So that's going to be equal to 3. Sorry, 1 second. Yeah, 3 plus, so this is 3 plus 4 t2. Okay, so that's for our x-axis. Now for our y-axis, we're going to have 0 plus 3t1. So 3t1 is going to be equal to 6 over here. So 6 plus, and then we're going to have, so minus 2t2. So minus 2t2. So that's for our y-axis. And then for our z-axis, so for our z-axis, we're going to have 1 plus 5t1. So 1 plus 5t1 is equal to 1 plus 7t2. So it's equal to 1 plus 7t2. Okay, now let's call these equations A, B, and C. And we're going to try to use equations A and B to solve for T1 and T2. And then we can try to plug it into equation C to see if these two sides are indeed equal. And if they are, then there will be a T1 and a T2. So there'll be 2 points. Let's say T1 is over here and T2 would also be over here where the equations intersect, and otherwise they won't. So let me erase these equations for a second. So in order to solve for T1 and T2, let's look at equation A minus equation B. So that will give us, so from equation A over here, we'd have this side minus this side, so that 3t1 and 3t1 would cancel, so you'd be left with 1 is going to be equal. And then on this side, you're going to have 3 minus 6, so that's minus 3. Plus, and then you're going to have 4t2 minus 2t2. So this would be 6t2. So plus 6t2. Okay, and this implies that, so we can move the negative 3 to the other side, get 4 here, divide by 6. So t2 is going to be equal to 4 over 6, which is 2 over 3. So that's what t2 is going to be. So far, any questions?
Hey, why are we subtracting A minus B again?
Because we want to only have T2 in the end. So if we subtract them, the T1s cancel. And then we can solve for T2 algebraically. Because the equation that we have in the end does not have any T1s in it, right? Only T2s. And then we can solve for T2. Yeah?
All right, word.
Okay, so now T1 over, so now let's try to solve for T1 over here. So let me just, so T1 is going to be, so let's divide by 3. So it's going to be 6 over 3, which is 2, minus 2 over 3, times T2, which is 2 over 3. Okay, and this is going to be 2, so 18 over 9, minus 4 over 9, which is equal to 14 over 9, right? And this is T1. So T2 is 2 over 3, and T1 is 14 over 9. So I'm going to just erase this for a second. So now if we want to know whether the lines intersect, we want to know if the z coordinates are equal. So let's plug it in. So is 1 plus 5 T1, which is 14 over 9. So 14 over 9. Is this thing equal to 1 plus 7 times 14 over 9? Sorry, times T2, which is 2 over 3. Right, and the answer is no, these are not equal. So, yeah, you can cancel the ones, try to solve this, and you'll see that you will not get the same result. So when the T1, when the X and the Y coordinates are equal for these points, the Z coordinates will not be. So, so these two lines don't intersect. Okay. So, yeah, in summary, the equation for a sphere is at the point A, B, C is x minus a, y minus b, z minus c is equal to r squared, z minus c squared, all of these squared, basically coming from the Pythagorean theorem or the equation for distance. And for a cylinder, we ignore the z coordinate if we want it to be infinite in the z axis, and we only restrict the x and the y axis. So we only do this for the x and the y axis. The magnitude, the distance between two points, if you want to find in R3, you can look at the vector between them and find its magnitude. So the vector between these points is going to be a squared, the component will be a2 minus a1, b2 minus b1, and c2 minus c1. And then we just square the components, add them, take the square root, and we get our magnitude. Then something new that we learned is the equation for a line. So if you have a point P0 and a vector V, you can define a line for it by looking at, so here's going to be my P0, and here's my vector V. And I can define this line over here by taking my line to be P0 plus TV. So that's this. And the parametric equations of the line will be the x component, y component, and z component. Okay, so let's continue with the dot product. Oh, whoa. Yeah, it looks like my computer froze for a second. A second. Sorry about this. Okay. Okay, so here, the dot product. So the dot product in general is used to find, for example, the angle between two vectors, so that you can use the dot product for, and projections. So we'll see what that means in a second, but let's first begin by looking at the definition. So if you have two vectors, v and w, so here, I'm going to go here. Okay, perfect. So let's say we have the vector v, which is equal to the vector v1, v2, and v3. And we have the vector w, which is equal to w1, w2, and w3. Then the dot product between them, v dotted with w, is going to be the first component of v times the first component of W plus the second component of V, V2 times the second component of W plus the third component of V times the third component of W. So that's going to be the dot product between two vectors. As you can see, it takes in two vectors. So in the slot over here, you would have two vectors, a vector and a vector, and it would output a scalar, some number. So it would output some number C. Okay, so we look at the definition over here. That's what we see. Here's my V, here's my W, and here is the dot product between them. So they ask us to take the dot product between 2, 3, 1, and -4. So dotted with -4, 2, and 5. So this is equal to 2 times -4, which is -8. And 3 times 2, so that's +6, and 1 times 5, so that's +5. And this is equal to 3. Okay. So in R2, the dot product is basically the same thing. And an important result is that if you take V and dot it with V, well, that's going to be, so again, let's say V is equal to V1, comma V2, comma V3, then V dotted with V is going to be V1 squared plus V2 squared plus V3 squared. And this is going to be equal to the magnitude of V squared. So V dotted with V is equal to the magnitude of V squared. So that's this over here. And we're going to use this in a proof in a couple of minutes. So now some important properties of the dot product is that it's commutative. So V dotted with W is equal to W dotted with V. And the reason for this is fairly simple. Again, let's say that your V is this, and my W is going to be W1, W2, and W3. Then my V dotted with my W is equal to V1, W1, plus V2, W2.
V3 is supposed to be cubed, or is that supposed to be squared?
This is squared. Here? Oh, sorry.
Left.
Sorry. Perfect. Thanks. Yeah, so you have V1 times W1 plus V2 times W2 plus V3 times W3. And then you can flip each one of these. So this is going to be equal to W1 times V1 plus W2 times V2 plus W3 times V3, which is, sorry, V3, which is going to be equal to W times V. I dotted with V. So we see that they're commutative. Other properties, you can either put the lambda in the V. If you multiply lambda times V, you can either put it in the V or in the W or keep it by itself. And this comes from the same exact type of proof that we just did for here, right? You just put the lambda in the components, you take the components and add them. So this is either lambda goes into V and then you have the dot product with W, or lambda goes into W, then you have the dot product with V, but this lambda can move. So yeah, same exact thing as 1. So that's for 3. And then you also have that it's distributive. So you can multiply this inside. And you have the relationship that we saw before. V dotted with V is equal to the magnitude of V squared. So they ask us to verify the distributive law for these 3 vectors, so that U dotted with V plus W is equal to U dotted with V plus U dotted with W. So let's try that. So for the first one, u dotted with v plus w. So your u is 4, 3, 3 dotted. And then you're going to have your your v, which is 1, 2, 2, plus your w, which is going to be 3, 3, a negative 2, and 5. So now if we're doing this one, we first want to add these two vectors. So this is going to give us 4, 3, 3 dotted with, and then 1 plus 3 is 4, and 2 minus 2 is 0, and 2 plus 5 is 7. So this gives us that. And then this is going to be equal to 4 times 4, so 16. Sorry, okay, I'm gonna go. Yeah. Okay, yeah, 16. Right, plus 21. Right, so this dot product, this times that is 0, that times that. And then this is going to give me 37. So when I do u plus dotted with v plus w, we get 37. For the other example, let's just look over here. We're going to have this times dotted with v plus my u dotted with my w. And they do the dot product over here plus the dot product over here, and they get the same result. So we see that for this example, the distributive law holds. Okay. Fine. One very important thing that we can do with the dot product is find the angle between two vectors. So let's first start with the following equation, and I'm going to show you how to prove it in a minute. But there's an equation that says that v dotted with w is equal to the magnitude of v times the magnitude of w times cosine of the angle between these two vectors. So if you have two vectors, here they are. This is the vector v, and this is the vector w. And they have some angle over here. So here's my angle between them. And I want to find this angle. Well, first we have the following equation. And this equation says the same thing as, one second, that v dotted with w divided by the magnitude of v times the magnitude of w is equal to cosine of the angle between these two vectors. Or another way to write this is that the angle between the two vectors is equal to cosine inverse of v dotted with w over the magnitude of v times the magnitude of w. Any questions about this? Okay, perfect. So here are those two equations. V dotted with w is equal to the magnitude of v times the magnitude of w times cosine of theta, or the cosine of theta is equal to v dotted with w over their magnitudes. So how do we prove this equation? We know that if we have a right triangle, then if we have a right triangle and C is the hypotenuse of our triangle, then C squared is equal to A squared plus B squared by Pythagoras' theorem. But if we don't have a right triangle, then there's a correction term. It's this term over here, negative 2AB cosine of theta. And so this C squared is equal to A squared plus B squared is basically the Pythagorean theorem. And then there's some correction term because we're not dealing with a 90-degree triangle. Now, Okay, so using this, we can look at the following triangle where this is W, this is V, and this over here is V minus W. So this is my C, and this is my A and B. So that tells me that V minus W, which is my C, is equal to A squared plus B squared minus 2 times the cosine, the magnitude of V and the magnitude of W. All of these are magnitudes because that we're looking for the length. A, B, and C are the lengths. So that's why we're looking at the magnitude. Now, if we look at one side of this equation, then this, because we know that the magnitude of V squared is equal to V dotted with V, we know that this is equal to itself dotted with itself. And then by the distribution, you can multiply the V's, so dot them, minus, and then do that 2 times V times W, W times V, so that gets you 2 of them, plus W times, or W dotted with W, so that gives you that over there. And this ends up being V squared, because this over here is V dotted with V, and W squared, because this over here is W dotted with W, minus 2 V dotted with W. But we know that this is equal to this side. So the V squared and the V squared can cancel. The W squared and the W squared can cancel. The negative and the negative can cancel. The 2 can cancel. And we are left with our equation that V dotted with W is equal to cosine of theta times V times the magnitude of V times the magnitude of W. Any questions about this? Is it clear? Hello?
Do we need that equation, or is that just showing the proof for what's in the red box beneath it?
So this was just the proof for this box, for this equation, that V dotted with W is equal to the magnitude of V times the magnitude of W times cosine of theta. So yeah, this is just the proof of that from here to here. So you don't need this as an equation, but it's interesting to know the proof. And it uses mostly the law of cosines.
All right, got it, thanks.
Yeah. So now we are left with the two equations, these two equations. Cosine of theta is equal to V dotted with W over the magnitude of V times the magnitude of W, or like I said before, that the angle is equal to cosine inverse of this over here. So let's look at the following example. So they want us to find the angle between the vectors V, this vector, and W. So in order to find the angle between them, we need to know 3 things. We need to know what V dotted with W is. We need to know what the magnitude of V is. And we need to know what the magnitude of W is. So I'm going to put that over here. So let's start with V dotted with W. So V dotted with W over here is going to be 3 times 4. So that's going to be 12. Plus 6 times 2. So that's going to be another 12. Plus 2 times 4. So that's going to be 8. So this is going to be 32. Okay. Now the magnitude of V is going to be equal to the square root of 3 squared, right, 3 squared, plus 6 squared, plus 2 squared, which is going to be the square root of 49, and that's going to be 7. So that's the magnitude of V. Okay, finally, the magnitude of W is going to be the square root of 4 squared plus 2 squared plus 4 squared. And that's going to end up being 36. So the square root of 36, which is going to be 6. So Now, in order to find the angle between these two vectors, we just use the equation that we have above. So we know that, 1 second, okay, the angle is going to be equal to cosine inverse of the dot product between V and W, so that's 32, over the magnitude of V, so the magnitude of V is 7, times the magnitude of W, so the magnitude of W is 6. So it's cosine of 32 over 7 times 6. Okay, and let me see. So that would be that. Yeah, 32 and 42, perfect. So any questions about this? Okay. So if two vectors, and a very important, a very useful fact about the dot product is going back to that equation, V dotted with W is equal to the magnitude of V times the magnitude of W times cosine of theta. Now, if we have two vectors, V and W, that are perpendicular to each other or orthogonal to each other, or the angle between them is pi over 2, this is my V, this is my W, then this is going to be 0, which means that V dotted with W is going to be equal to 0. So anytime I have two vectors that are perpendicular to each other, their dot product is going to be 0. So that's what they tell us next, that if you have two vectors, V and W, that are perpendicular or orthogonal, meaning that there's an angle of pi over 2 between them, then V dotted with W is equal to this, which is equal to 0 if my angle is pi over 2. And so these are perpendicular. And so we can do some examples with I, J, and K. I, J, and K are definitely perpendicular to each other. So if you have the following axis, X, Y, Z, then this is your I, this is your J, and this is your K. So they're definitely perpendicular to each other. Now I is equal to 1, 0, 0. J is equal to 0, 1, 0. And K is equal to 0, 0, 1. So I dotted with J, for example, is going to be 1 times 0, 0 times 1 plus 0 times 0, so it's 0. And J dotted with K is also going to be 0 times 0 plus 1 times 0 plus 0 times 1, so it's also going to be 0. So, and that would be true for I dotted with K and so on. So these are orthogonal to each other. Okay, so now they want us to tell them whether the following vectors are orthogonal to each other or not. So if the vector V is this, we want to know if it's orthogonal to U and whether it's orthogonal to W. So let's look at V dotted with U. So V dotted with U is 2 times 2, so that's 4. And then you're going to have minus, so then it's 1 times 6, so it's minus 6. And then 1 times 1, so it's plus 1. So this gives us negative 1, so they are not orthogonal. So yeah, not orthogonal. And then V dotted with W. So that's going to be 2 times negative 4, which is going to be negative 8. And then it's going to be negative 1 times 1. So it's going to be minus 1. And then it's going to be, oh, sorry, I'm doing it between two other different vectors. Okay. V dotted with W. Sorry about that. Okay. So now it's, yeah, negative 4 times 2. So it is negative 8. And then it is 6 times 1, so plus 6. And then it is 1 times 2, so plus 2. So this is 0, so they are orthogonal. So yeah, they are orthogonal. So now they say that we can define what it means for an angle to be obtuse and acute based on whether the dot product between them is less than 0 or bigger than 0. But it's not very important in multivariable, I don't think. So I'm going to ignore this example, testing for obtuseness and acuteness. And I'm going to move on. And I'm going to ignore this example as well. So yeah, I want to continue with projections. So that's over here. Okay, so projections are very important. And what we are trying to do is we're trying to take two vectors. So here's my vector v. And here is my vector w. And we want to project w, let's say, onto v. To get another vector that goes in the direction of v, but has the magnitude of this vector over here, which is the projection of w onto v. And we're going to call this the angle between them. Okay, so yeah, that's this picture over here. So here's a u, here is v, and the notation that they're using is that u, 2 lines v, means that u is projected onto v. We also say that this is the projection of u onto v. So that's this picture over here. But you can also have a projection like this. If v and u are going in different directions, then the projection, you can't really project u onto v, but you can project it onto this line. You can imagine that we extend v into a line, and then we project it. So we can still talk about the projection of u onto v, even if they're going in two different directions. Any questions about this? Okay, so a good way to do this is first find the component of this vector over here. So first find the magnitude of this vector, and then we can look at EV. So EV is the unit vector of V. So we kind of shrinks V down. Let's say this is EV. And then we can multiply EV by the component of the projection of U onto V. So we multiply it by comp of the projection of U onto V. Okay, 1 second. Yeah. Okay. Here, let me go here. So, yeah, let's imagine here's my U, here's my V, and I am trying to find this over here, which is the projection of U onto V. So first, it's useful to find the component of this projection. So not the vector, but just this length. So that's going to be the component of the projection of U onto V. Okay, a good way to do this is by imagining that your x-axis goes right through V. So your V sits on your x-axis. So here, sorry, x, y. And I'm just going to put the V right down here in such a way that U just appears here. Now, if I wanted to find the component of this projection, if I wanted to find this over here, this red part, well, that's going to be the magnitude of U times cosine of theta times cosine of this angle, right? So that's the component of the projection of u onto v. Okay, so now if I wanted to find the projection itself, so the projection u onto v, projection of u onto v, this is going to be equal to this component times EV, times EV. So again, what we're imagining is that we found the component of this projection, and then we look at the unit vector. So you look at the unit vector over here, EV, and then you just multiply it by this component, so by the red part, and you get the green part. You get your projection. So far, is this clear?
Yep, looks good.
All right. So now this over here is equal to the magnitude of u times cosine of theta times 1 over the magnitude of v times v. Right? Because this over here is just EV. Okay. So now you just multiply the top and the bottom over here by v, by the magnitude of v. So this is going to be equal to the magnitude of v times the magnitude of w times cosine of theta times 1 over the magnitude of v squared times v. And now this over here is v dotted with u. So this is going to be equal to v dot u over the magnitude of v squared times v. And that's what u is. That's what the projection of u onto v is. So if you look here, this is the proof that we just went through. So the projection of u onto v, first you look at the component of u in the x direction. So that's why you have cosine here, times the unit vector. And this is going to be equal to this. You just look at what the unit vector is. And this is equal to uv cosine of theta divided by the magnitude of v squared times v, which is equal to the dot product times v dotted with v, or the magnitude of v squared times v over here. Now, so here, the projection of u onto v, a very easy way to remember this, in my opinion, is by remembering what the component is. So the component of the projection of u onto v is equal to the dot product of u dotted with v over the magnitude of v, over the magnitude of v. And so then the projection of u onto v is going to be this component, so it's u dotted with v over the magnitude of v times the unit vector, so times v over the magnitude of v, right? And this is equal to u dotted with v over the magnitude of v squared times v. So yeah, the component, again, there are two parts here. There's the component of my projection, and there's the unit vector in the direction of v. And this is actually the important thing to find, and this is the much easier thing to find. But as you can see, the dot product is used in the projection because the dot product kind of represents cosine, right? Again, v dotted with w is equal to the magnitude of v times the magnitude of w times cosine of theta. And cosine allows you to take lines and project them into the x-axis. So it allows you to find this. And that's why even if my vectors are a little, skewed, I can still imagine that this is my x-axis, project this thing down, find this component, find the unit vector of this vector, and that's how I can find my projection. So that's a very big use of the dot product, is to, instead of using cosine, you get to use the dot product. So the dot product can always replace cosine, actually. So now, let's look at the following example. We want to find the projection of u onto v over here. So in order to do this, we need a couple of pieces of information. We need to know what u dotted with v is. So what is u dotted with v? So that's 5 times 4, so it's 40 plus, and then we're going to have 4 times 1, so that's 4 plus, and then we're going to have negative 3 times 2, so that is minus 6. And this is going to be equal to 18. Now, another piece of information that we need to know is what is v dotted with v, or what the magnitude of v is, and then we just need to square it. So this is going to be, so the magnitude of v, okay, this is just going to be 4 squared plus 4 squared, second component, plus 2 squared. And we don't have the square root, because we remember that the, let me just do it over here. Yeah, the magnitude of v squared is equal to v dotted with v. So yeah, so when we look at v dotted with v, we don't put the square root. Okay, so now that we have these two pieces of information, we know that u projected onto v is going to be equal to this dot product, so that's 18, over this dot product, so that's going to be, sorry, so this is 36. So over 36 times v, times the vector v, whatever that is. And yeah, so this is 18 over 36. Sorry, yeah, oh, yeah, times v, perfect. And that ends up being 2, 2, 1. So that's what the vector that we end up getting. Okay, is this understood?
Yes.
Yeah. Okay, so another thing that we can do, but again, this is not that relevant to multivariables, so I'm not going to spend that much time with it. But instead of looking for the projection, so here we can look at this picture. Instead of looking for this projection, we can look for the component that we lost during the projection. So that's this component. It's really this vector over here. In order to get to the vector u, you can put this vector over here and then add a vector to its tail. So u really is equal to u with the projection of u onto v plus this vector over here, which they're going to call u perpendicular to v. So the component of u that's perpendicular to v. Okay? And that's how the vector u can always be written. It can always be written as the component of u projected onto v plus the component of u that is orthogonal to v. But like I said, I'm not going to spend that much time on this, especially because that this component, the component orthogonal to v, is just equal to u minus the projection. So once you find the projection, you can find the component that's orthogonal to it, and then you can always decompose u into the projection part and into the orthogonal part. And that is what this example is doing. But again, I am not going to focus on this because it doesn't appear that much in multivariable. If you have like homework questions or a question appears with this problem and you're having a difficult time with it, please yeah, let me know. And then over here we have a physics example. So I'm going to, sorry, yeah, physics example. I am going to skip this one as well but you're trying to find the components of the force in different directions. And again, another physics problem when you're trying to find the components of the force in different direction. We're not going to focus that much on this, so I am going to skip those problems. Okay, and then to summarize the dot product, here's the actual definition. It's commutative, as we saw, distributive. V dotted with V is equal to the magnitude of V squared, and V dotted with W is equal to. So this is the most important equation that we saw today. The connection between the dot product and trigonometry. Yeah. Okay, so I'm going to stop here. Are there any questions? Any questions about the class, the material, anything?
When do we have quizzes in this class?
So there's going to be a quiz either on Tuesday or on Thursday, but it's not going to be in class. I'm just going to post some paper on Canvas, and you're just going to have to scan your work and submit it on Canvas.
For that quiz, can we just do it on notebook paper and like scan in pictures like that, or do you want it on that?
Yeah, anyway, any whiteboards, anything works, yeah, as long as we have the material, yeah.
Okay.
Anything else?
So that quiz would be next week.
Yeah, it's going to be next week. It's probably, it's going to be on dot products and cross products, maybe a little bit on lines. And yeah, so there might like be a projection problem, or we're going to see how to find the distance between a point and a plane. At least we might see that this week. So a question like that might appear, like find the distance between a point and a plane. Actually, because we did projections, we can do those type of problems. So yeah, next class I'm gonna continue like talking about projections, and then the class after I'm gonna start talking about cross products, and then we might continue on Tuesday, and then maybe Thursday we're gonna have a quiz, and it will be due something like Friday. Maybe it'll be a quiz for Friday, and it will be due Friday, and that'll be that. And then yeah, you're also gonna have homeworks this week and next week, so try to do those on time.
So will a good way to prepare for those be just to go over the problems that we did in class?
Yes, yeah.
Professor, I have a question.
Yeah.
This is my first class. I just enrolled, and I was wondering if you could point me in the direction of some videos to like catch up.
Yes, so I posted some videos myself, and you can find them on YouTube. I mean, go to Canvas and you can find a link to them. And then there are many multivariable calculus videos. There should be, maybe I haven't posted these, but someone is making like multivariable calculus videos for Penn State this semester. So I might add a link to that, but you can go onto YouTube and find a lot of different videos.
Thank you.
Oh, and also, yeah, try to do the homework problems, because like, the quiz problems can be similar to homework problems, or they can be similar to problems that we did in class. So yeah. Okay, any other questions? Oh yeah, perfect. So have a nice day. I'm going to try to post this recording at some point. Yeah, have a nice day. Bye.